All right, so today we're going to wrap up the chain rule. This is just a review day where you will use the chain rule to take the derivative of trig equations and rational equations. So let's go ahead and take a look at this first example here. It says find the derivative of each of the following. If I were to plug in a number for x, what's the first thing you would do? You would square it, okay? And then once we get what that angle measurement is, then I would take cotangent of whatever that angle is. So it's like unwrapping a gift when we do the chain rule. We want to start with our outermost function first. So that's going to be cotangent. And then we're going to have to multiply by the derivative of the innermost function, which in this case would be x squared. Okay, so we are using chain rule on this. My outer function is going to be cotangent and my inner function is going to be x squared. So I need to know what the derivatives are of each of those. So what's the derivative of cotangent? Well, if I look back on this cheat sheet, it looks like the derivative of cotangent is negative cosecant squared. So I'm going to just note that. Let's do that. Negative cosecant squared u. And then the derivative of x squared would be 2x. So let's go ahead and use a chain rule to find the derivative now. We're starting by unpacking the cotangent first, which the derivative of cotangent is negative cosecant squared of u. Right? So x squared does not change there. And then I multiply by the derivative of the inner function, x squared, which would end up being 2x. So my final answer for my derivative, once I combine the 2x with the negative 1 out front, right, we multiply those together, we would get negative 2x cosecant squared of x squared. Okay, because it's a monomial, you can put this in parentheses if you want to, but you don't have to. All right, looking at the second example here, looks very, very similar. What's the difference though? Here, the squared's on the end, where here the squared comes right after cotangent. That does change things. Really, I could write this as cotangent of x quantity squared, and that's equivalent. So now let's think about it. If I were to plug in something for x, what would I do first? Well, first, what I would do is I would take the cotangent of whatever x is, and then once I get that inner part simplified, then I would square the expression. So remember, when you are differentiating, you got to go the opposite direction, unpack that gift. I need to think of the squared like it's my outermost function, so I'll highlight that in blue, and I want to think about cotangent like it's my inner function. Okay, so we've got two layers here. I've got u squared as my outer layer, and then my inner layer is cotangent x. So the derivative of u squared would be 2u, and the derivative of cotangent x, let's remember, is going to be our negative cosecant squared. Okay, so let's go ahead and differentiate. I'm going to put y prime here. We start with that outermost function. If I bring the 2 out front, I copy cotangent exactly how it is, and then I subtract 1 from the exponent. That's going to be the derivative of my outer function. We can mark it off. Then we multiply by the derivative of the innermost function, which the derivative of cotangent x is going to be negative cosecant squared x. Simplifying, we multiply the 2 by the negative 1, so we'll get negative 2. Then we have cotangent x, cosecant squared x. And I like to make sure that this is the most simplified form. If I were to rewrite cotangent, cotangent's going to be cosine over sine. And cosecant squared would be 1 over sine squared. So see how there's no signs that cancel out? Like if this had said tangent and not cotangent, like let's pretend that had said tangent instead, then it would have been written like this. Sine over cosine, which then you could probably simplify a little bit, right? One sign from up top with one sign from below. You always want to check and make sure there's not a more simplified answer that you can provide. But in this case, there's not. Okay, and look at the differences between these two answers. Okay, they are different. So you have to pay close attention to what's your outermost part of your composite function and what's the innermost part. It does matter. Okay, in example 3, I'm going to rewrite this as y equals sine of x to the 1/2. Okay, so really if I were to plug in something for x, what would I do first? I would raise it to the power 1/2. We would get what that angle is, and then I would take the sine of it. So if I'm unpacking that, going in the reverse order, my outermost function is going to be sine, and then my inner function is going to be this x to the 1/2. Okay, so my outermost function is sine, and my inner function is x to the 1/2. Remember, the derivative of sine is going to be cosine. And here, if I take the derivative, we get 1/2 x to the negative 1/2. Okay, so let's go ahead and find the derivative. The derivative of sine is going to be cosine u. So I keep that angle the exact same. Notice that the x to the 1/2 didn't change. Then I multiply by the derivative of the inner function, which the inner function's derivative would be 1/2 x. And then if I subtract 1 from this exponent, we get negative 1/2. Okay, and then that's done. Simplifying, we get cosine x to the 1/2 times, this is going to be 1/2x to the 1/2, right? I've got to fix that negative exponent. Let's go ahead and rewrite it in radical form just to clean this up a little bit. We get cosine root x over 2 root x. Now be really careful here. These root x's don't cancel. This root x in the numerator is the angle for cosine. So all of this is attached together. You can't break it into parts. It's not like it's being multiplied, right? You can never have cosine and then not have an angle written in. That angle is attached to cosine. Okay, so that's going to be it. That's going to be our answer. Let's go ahead down here. Rewrite this. We have y equals sine x to the 1/2. Okay, so now 1/2's on the outside. Again, it looks similar to what we saw up here in example 3, but notice that position of the square root changed. If I plugged in a number for x, what would I do first? First, I would take sine of whatever that number is, and then I would raise it to the power 1/2. So going in the reverse order, or unpackaging that present there, you got to take off the 1/2 first. It's going to be outer function, and then sine x is going to be our inner function. Okay, so we need to differentiate in that order. We've got u to the 1/2 as our outer function, and then we've got sine x as our inner function. Okay, so this would end up being 1/2 u to the negative 1/2, and the derivative of sine is going to be cosine. Okay, so when I write the derivative, we take the derivative of the outer part first, so the 1/2 would come down. Sine stays the same, right? Sine x stays the same. We subtract 1 from the exponent, so we get negative 1/2. And that completes the derivative of the outer function. Then I have to multiply by the derivative of the inner function, which is going to be cosine x. Let's go ahead and clean up those negative exponents. We get 1/2 times the square root of sine x times cosine x. So now the cosine x goes up top. We have cosine x over 2 root sine x. All right, wonderful. Over here, let's start by just rewriting this. I see this squared, so I know really this is what it means. We have sine of 4 theta, and we're squaring that whole quantity. Okay, just rewriting it's going to help me figure out my layers. If I were to plug in something for theta, what would I do? Well, I would first multiply by 4, right? So we have this layer. Then once I multiply by 4, then I would take the sine of it. Then once I've taken sine of that angle, then I would raise it to the 1/2 power and multiply by 1/3. So really, we've got a 3-layer problem here, right? My outermost layer is going to be, let me go ahead and highlight it, squaring and multiplying by that 1/3. That's my outermost layer. Then we've got our secondary layer, which is sine. And then we've got our innermost layer, which I'll do in green. That's going to be our 4 theta. Okay, so 3 layers. We've got 1/3 u squared. That's my outermost layer. We've got sine, we'll just call it u again, sine of something. And then we've got 4 theta on the innermost part. Okay, so here if I take the derivative, we would get 2/3 u to the first. Here if I take the derivative, we'd get cosine. And here if we take the derivative, we would end up with just 4. Okay, so let's go ahead and differentiate this now. Starting with my outermost function, 2 times 1/3 is going to be 2/3. That inner part stays the same, so we've got sine of 4 theta. Then we subtract 1 from the exponent, so we get to the first. Okay, so that outer part is done. Then we multiply by the derivative of sine, which is going to be cosine of that same angle. Notice 4 theta doesn't change. And then I've got to multiply by my innermost layer's derivative, which the derivative of 4 theta is just 4. All right, so here's what we've got. What is 4 times 2/3? That's going to be 8/3. Sine of 4 theta, cosine of 4 theta. And we're really not done yet because that's a double angle property, right? This is a double angle. Double angle formula is something we can use here. I'm going to take half the leading coefficient. So if I divide this by 2, we'd end up getting 8/6, which we can reduce in a second. We write the word sine, and then I double the angle. So if I double 4 theta, it's going to give us 8 theta. So really for my final answer here, see 8 and 6 are both divisible by 2. So I'll get 4/3 sine of 8 theta. That looks good. All right, last but not least, example 6 over here. Let's think about if we were to plug in a number for x, what would we do? Well, I'd simplify this inner part first, and then I would square. So this is going to be a combination of chain rule and quotient rule. My outermost function is going to be squaring, right, that u squared. And then my innermost function is going to be this x squared plus 1 over x minus 2. Okay, so on the outermost function, that's going to be pretty straightforward. We get 2u. But on the innermost function, that's going to be where we have to use the quotient rule. Okay, so let's start with our outer function, which is the squaring, and then we'll get to this inner part later. All right, g prime equals, we go ahead and multiply the 2 by this leading coefficient of 1. We get 2 x squared plus 1 over x minus 2. And then we subtract 1 from the exponent. So that part's done. Then I have to multiply by the derivative of the inner part, which the derivative of the inner part we know we're going to need to use quotient rule on. We take the derivative of the top times the bottom minus, and I'm going to run out of room, so I'm going to just squiggle this out, erase it. Okay, so again, we have derivative of the top times the bottom minus, then we have the top times the derivative of the bottom all over the bottom squared, right? You might hear some of your friends say this, the low d high minus high d low over the low squared. It's a fun little jingle that people say. Again, it's low d high. D means derivative of the higher expression, minus high d low over low squared. I'll say it one more time. We have low d high minus high d low over the low squared. Okay, let's go ahead and simplify this now. We have 2 times, we'll say x squared plus 1 over x minus 2 times, let's go ahead and simplify the numerator here. If I distribute 2x through, I get 2x squared minus 4x. Here, if I distribute the negative 1 through, we get negative x squared minus 1 all over x minus 2 squared. So we'll have 2 times x squared plus 1 over x minus 2 times, what's this going to end up being? 2x squared minus x squared is just going to be x squared. And then we still have the negative 4x minus 1 all over x minus 2 squared. X squared minus 4x minus 1, that doesn't factor. So I'm going to go ahead and just multiply straight across. We've got 2 x squared plus 1 and x squared minus 4x minus 1 factors in the numerator. And here when we multiply like bases, don't forget we have to add the exponents. So I would add the 1 plus 2 exponents together. So we'll get x minus 2 cubed. Okay. And that's it. Try the back on your own.